Hello and welcome to our very first video on system controls. Today we're going to have this asynchronous module on system stability, which is chapter 5 in Owen's book. As you saw, I've created a OneNote file that's already pre-written largely, and so in today's lecture I'm going to be going over that file and adding comments and clarification as we go along. Okay, stability. First, let's start with a definition for stability. Stability of a system, you probably already have a fairly accurate, intuitive understanding of what that can mean. And it simply means that a system a system's response will decay to zero if the system is stable. In other words, will reach a steady state value over time. And the system is unstable if it does otherwise. In other words, if the system's response grows indefinitely with respect to time. So that follows our typical understanding of stability in layman's life. Now, of course, there's a special case here that is worth highlighting is if the system neither grows nor decay, then we say that the system is neutrally stable, or neutral, or marginally stable. Those are all synonyms. Let me plot these cases on the side here to give you kind of an idea, although I think you can probably largely do this on your own already. Let's put one here. I'm going to stick with black here, I think. Okay, let's put another one down here for unstable. And finally, let's put a third one here for marginally stable. So let's say that in all three cases, I got myself an input that's a step input. So boom, this is what I'm doing. And let's say that the gain is 1. So the system and the unit response are on the same scale. So therefore, I can, at steady state, if the system is stable, I'm going to merge onto that or asymptote towards that red line. And I'm going to use that for all three of my cases here. Oh, shoot, it looks like my third one stuck with the red. I don't know why I did that, but we'll live with it. Here's that red one. 1, 2, 3. Okay. All right. So what I've just plotted here, of course, is the input. So R of t, a step input. And now what I'm talking about is the response to that system being stable or unstable. And because what we're most familiar with at this point is a first order system, I'm going to do a first order response to this. So in the case of the stable first order response, I'll start with that. So the response C of t would look like this. And you already expected that, right? So that would be my C of t stable. If the system is unstable, grows indefinitely, it's going to have a response that looks like this and goes to heaven, to infinity. Okay. I can't do the marginally stable system for a first order. I'm not aware that that's even defined. So instead, what I'm going to do now is overlay on top of these two first graphs what a second order stable and unstable system looks like. And then I'll do the marginally stable, which is properly defined on the third graph. So let's change color here. For the stable system, second order system, the response is going to look like that. Concave up right at the origin, overshoots the axis and starts to oscillate, and eventually reaches the same steady state as the input, right, for my gain of 1. For the unstable system, what's going to happen is I'm going to have response that's going to grow over time and go away like that. And for the marginally stable system, I'm going to have a response that's going to look like this. I have here 1.5, 2. My graph as clean as possible. So you see the amplitude of oscillation does not decay with respect to time, remains constant. If I were to plot it over here, it would be 2 parallel lines to my steady state value, but they never converge towards it. So the response remains like that indefinitely. And so those are my three different possibilities in the case of a second order system. Okay, so a stable system decays to a steady state, an unstable system grows indefinitely, and a marginally stable system has a finite amplitude of oscillation that does not decay. Now, we've already saw and talked about the general form of the second order system, if you recall, and that's, I think, in your chapter 2 in your book. And the general form of it is K assessed, or steady state gain, times the natural frequency squared divided by S squared plus 2 zeta omega n S plus omega n squared. And it's time to look at different cases now for that second order system in terms of stability already. Specifically in the case of the underdamped case system, which is the one that was oscillating as I had above, that corresponds to a value of zeta, the damping ratio between 0 and 1. Okay, so that's the what we call the underdamped case system. And its characteristic equation, which we've defined in a previous class, is the denominator of g of s, and I'll repeat this a little bit later. The denominator of g of s set equal to 0, so that means s squared plus 2 zeta omega n s plus omega n squared is equal to 0, which of course is a quadratic equation in S. And in the case where zeta is between 0 and 1, then the roots of that quadratic equation are going to be complex, complex numbers, so they'll have an imaginary component. Why? Because the radical of that quadratic equation, namely b squared minus 4ac, is equal to is equal to 2 times the natural frequency times the square root of omega squared minus 1, which itself is a negative number, right? So do we need to highlight that there? Maybe it's worth highlighting it a little bit here. So this here is our the characteristic equation is the denominator of the g of s term, and it's of the form a s squared plus bs plus c is equal to 0. I know it's been a long time since you've played with quadratic equations, since high school probably, so that little exercise is not a waste of time maybe. And in this case we've got a is equal to 1, b is equal to 2 zeta omega n, and c is equal to omega n squared. And if you recall from your study of the quadratic equation, the roots or the zeros of that equation, I'm going to try and not use the word zeros because, as you know from our previous conversation, which again I'll repeat in a moment, when we say zeros in a context of control systems here for a system, I'm really talking about the roots of the numerator, and poles refer to the roots of the denominator. And here, of course, with the quadratic equation, I'm dealing with the denominator. But still, the roots of the denominators are going to be, okay, the roots of this quadratic equation, which are also the poles. There are going to be S, and there's going to be 2 of them, 2 S's for which this characteristic equation is equal to 0. So I'll call them the first root I'll call S1, and the second one I'll call S2. But I'm going to write them both together here. They are minus b plus or minus the square root of b squared minus 4ac divided by 2a. This is what you spend, I'm sure, lovely time in high school studying to death. So that is equal to minus 2 zeta omega n plus or minus b squared, which is going to be 4 zeta omega n squared, minus 4 times 1 times omega n squared, square root of, divided by 2a, and that's what I did over here for the radical. So that is going to be equal, oh sorry, a is 1. There we go. That is going to be minus zeta omega n plus or minus the 4 square root of 4, which I factor out of there, goes on the outside of the radical, divided by 2 is just going to be 1. So I'm going to have, and same with the omega n, comes out of there, omega n times zeta squared minus 1 square root of. So those are my two roots for the quadratic equation. Okay? All right, but for the time being, I just care about this guy right there, the guy that gives me this imaginary response, and that is actually what causes the system to be oscillatory for damping ratios between 0 and 1. All right. Now, that system is going to be stable even if it is oscillatory, meaning if zeta is between 0 and 1. If, as we showed on that little graph above, that oscillatory response drops over time, decays over time. Okay, so let's define a few terms here, and it's not the first time I'm defining them, but they're so important it's worth repeating, that are going to form the basis of our analysis on stability as well. And we're going to start talking a lot about these particular terms because as I said, they're going to come up a lot when we talk not just about stability, but about control systems in general. Let's start with our very basic control system here, which is a reference input coming into a plant. The plant system is denoted as G of S, and the output of the input inside that plant is C of S. First, the zeros of both R, the input, G of S, the plant system, and C of S, the output, are going to be the roots of the numerator of these three different functions of S. The poles of R, G, and S are going to be the roots of the denominator. Okay. The system zeros and system poles are going to be specifically the zeros and the poles of G of S. So G of S is so important, it has its own sort of name. Although, as you saw from the first two lines, I can also refer to the system poles and zeros as zeros and poles as well. The system characteristic equation is the denominator of G of S, all right, the polynomial in S. Now, pretty soon we're going to be plotting these guys, these poles and zeros, mostly for the system. So the system zeros and poles, we're going to plot those on a graph. And just so that you're getting ready to think about this, give you something to think ahead a little bit, the zeros on that graph are going to be denoted by zeros. Okay. The poles on that graph, so I'm going to say denote on plot as 0 for zeros, X for poles. It's almost like a game of tic-tac-toe. And yeah, so those are going to be important actually. Yeah, so those are going to be how we're going to delineate between zeros and poles on our plot later on. Okay. All this is important because the analysis of the of the system characteristic equation and its zeros and poles are going to be the first step to our stability analysis. All right. So far, so good, right? We've defined stability for both a first order and second order system in terms of stable, unstable, and marginally stable. We've reviewed a little bit what it means for the system's characteristic equation for a second order system, what it looks like. Okay, what it needs for the system to be unstable in terms of zeta, what that does, and what that does to the poles of the characteristic equation, the roots of the characteristic equation when that's the case. All right, so next, let's talk about plotting those roots for the characteristic equation, so the poles of their system. Because zeta can be really anything. If it's greater than 1, an overdamped system, there's really nothing particularly interesting about the roots of the characteristic equation, right? They're going to be two real numbers, and when we say plot them, you're really putting them on a straight line, a real axis, and you'd be done. But because for an underdamped system, zeta can be between 0 and 1, and we have this imaginary component to now the roots of the characteristic equation, if we want to put them on a graph, we're going to need to have a complex plane to do so. And the graph that we specifically use to do this is what we call the S-plane. The value of all possible roots to all different types of system characteristic equations, defines the entire range of the S-plane. And so I've just plotted one right here. Notice that the y-axis, as you may be familiar with, represents the imaginary axis. Imaginary is denoted by IM. That's my y-axis. Similarly, the real axis, which is denoted with a funny double-legged R, that's my x-axis. So my poles represent a couple on that particular plane, on that S-plane. Okay, let's start with the first order system, which, as you know, can be represented with a transfer function of steady state gain divided by tau s plus 1, where tau is that first order system's time constant. Okay, and let's just say, for the sake of discussion, that particular system has a, well, actually, based on what we're seeing here, written in this form, the characteristic equation is going to be tau s plus 1 is equal to 0. And so, therefore, we're going to have a pole at s is equal to minus 1 over tau. Okay, a single pole, first order system. You have as many, oh, that's an interesting observation too, right? I should probably highlight that there. Have as many poles as the order of the characteristic equation. This is a note to highlight. Okay, so first order system, we're going to have one pole. In this particular case, well, it's going to be 1 over tau. It's always going to be 1 over tau, really. But assume that I have picked a specific tau. And so that tau falls on my graph as I've got over here with this x right there. This is my 1 over tau, minus 1 over tau. I'm on the left-hand side of the S-plane. You notice I'm on the real axis on the left-hand side of the imaginary axis on the real axis. I'm going to call that the left-hand side S-plane. And we're going to see that that's an important criteria for stability, that S-plane, and where we are on that S-plane. Specifically, we're going to want to be on that left-hand side S-plane. Now, there's more to it than just stability when we look at the roots of the characteristic equation on the S-plane. The further we are on the right of that left side S-plane, in other words, if I grab this guy, minus 1 over tau, and I move it towards the imaginary axis, then the slower the response of my system is going to be. Okay, the slower it's going to take for my first order system to reach steady state. The further out to the left I am, on my S-plane, then the faster the response of my system is going to be to a step change. Okay, so this is telling us a lot of things already about how the system behaves. Um, if the system pole of a first order system is very close to the y-axis, it kind of, what it's telling us is it doesn't really want to go to a steady state. It's already a bit of a hint. Whereas if it's very far from the imaginary axis on the left, then it reaches that steady state very, very rapidly. So 1 over tau is really an indication of the speed of response of the system. So bear that in mind. Now, specifically, if we have a system where the steady state gain is 1, then its step response, as we saw before, at the very, like around week 1, week 2, when we looked about the tank problem, is going to be C of t is equal to 1 minus e to the minus t over tau. Right? Remember this? We derived all this both from a basic ODE point of view, and then we repeated it from a Laplace transform point of view, and we found that the step response was given as that. Now, if for some reason tau was negative, meaning that 1 over tau was negative, whatever that means, right? Negative time is not possible, but if mathematically we define the characteristic equation to be in that way, then 1 over tau would be less than 0. Then the system would grow indefinitely, as we saw in that very first graph on the top. And more importantly, the pole of that characteristic equation would be on the right-hand side of the S-plane. And the characteristic equation itself would be S minus 1 over tau is equal to 0. Okay? And so these are two great hints that our system are going to be unstable. Again, if that root is on the right-hand side of the S-plane, okay, and the characteristic equation looks like this, S minus 1 over tau, then our system is unstable. And the two hints that we have is, first, that there is a pole on the right-hand side of the S-plane, and the second hint that we have is that there is a sign change on the coefficients of the characteristic equation. So the first coefficient that we have on the characteristic equation is a +1, and the second coefficient that we have on the characteristic equation is minus 1 over tau. So we went from plus to minus, and that sign change on a first and second order system or on any system actually is an indication that the system will in fact be unstable. We don't have to do any more work than that. I give you a characteristic equation, there's a sign change somewhere, stop, and the question is the system stable or unstable? You can stop, system's unstable, done. Don't have to do anything else. All right, so keep those two things in mind. You see a pole on the right-hand side S-plane, unstable. You see a sign change on a characteristic equation, unstable. So that's already two important tests that we have here for stabilities. So let's go back to the second order system. We started talking about that a little bit. And one of the things we're trying to do here is develop these stability criterions here to determine if the system is stable. So here's a general form of the system transfer function, and again, the characteristic equation. We've already established that the poles or the roots of the characteristic equations are this, right? Let's go back and verify this here. Okay. We found that our poles were minus zeta omega n plus or minus omega n times the square root of zeta squared minus 1. And that couple right there, that group, is what we call the damped natural frequency. So damped natural frequency is equal to natural frequency times zeta squared minus 1 square root of. Okay? And so that's what we've got down there.
Okay, oops, sorry, actually, the damp natural frequency is not zeta squared minus 1. That's incorrect. Let me correct this. It is 1 minus zeta squared. Okay. So therefore, this whole guy right there, omega n times zeta squared minus 1 is equal to j, the complex number, square root of 1, times omega d. Okay, and that is what I got down there. And now we're in good shape. Okay. So if omega n and zeta are both positive number, as you'd normally expect on most passive regular systems, linear systems certainly, then that system's always stable, right? Always stable. Why? Because the roots of that characteristic equation, the roots of the quadratic equation that we found up there are going to be on the left-hand side of the S-plane, because this guy here is going to be less than 0 always. So the real component is on the left. Done. We're finished. Okay. And what is the overall response of that system? Well, consider a step input of magnitude 1 over s with a steady state gain of 1. So a very basic system with those parameters. Then the output of that system is going to be C of s given as we've got here, omega n squared divided by s times s squared plus 2 zeta omega n s plus omega n squared. You can separate that into partial fraction, which is what I've done over here, and you can solve that. And when you do that, you're going to find that you have three roots to this system, right? One that corresponds to the step input, and that's the guy that's lying right on the origin. Okay, no problem. And two additional roots, that correspond to these two guys right there. The second and third term on the partial fraction expansion, which I'm denoting their zeros here as S2 and S3, and those corresponds to S2 is equal to minus zeta omega n plus j omega d, and that's what this guy is. And S3 is the same thing with a minus j omega d right there, and that makes the denominator go to 0. And voila, that's the graph that I have on the S-plane of the three roots of that step hitting my system right there. So if you find the actual solution there after you invert this Laplace transform, you're going to get an answer, which is the physical response of the system in the time domain. And I want to highlight to you here a typo in Owen's book. This is the way he's got it written here for that particular response, at least in chapter 5. That is incorrect. The proper response should be like this. Okay? So this is what that partial fraction expansion solution inverted back into a time domain looks like. So this is the generic form of the response of a second order underdamped system looks like when subjected to a unit step input. And it's a very important system. And this is really what I plotted at the very beginning here when I showed you what the stable response of a second order system looks like. Okay, and in the case of the marginally stable system, the one that never decays, that's when zeta is equal to 0, and that term blows up right there. That's part of the reason why that is important here. So anyway, so that's what we've got there for the second order system. All right. Negative damping. Now, this is not something that's intuitively very obvious, but it sometimes happens when, for whatever reason, in a real model, in other words, a model that is not truly linear, then the second coefficient of the characteristic equation becomes negative. So the zeta becomes negative.
So it's very often the result of a nonlinearity in the system characteristics. Sometimes it's the result of active control within a system that basically acts as a negative damping within the system, and that will cause theta to appear to be effectively negative, and that makes the system unstable. So now we're going to have some poles on the right hand side of the S-plane, and mathematically it means that the solution to C of t is going to have a term, because zeta is negative, of the form e to the plus at, that determines its time response. Well, if it's equal to plus at and a is a positive number, then of course as time grows, e to the at is going to grow indefinitely, and so the response is going to blow up, right? So that's your criteria for instability in a second order system. All right, so let's summarize a little bit what we've got here and start buttoning down our test for stability a little bit more rigorously. So any system with a pole on the right hand side of the S-plane is going to be unstable. Even just one pole is going to be enough to guarantee instability. Okay, nothing else matters. So this graph that I drew for you for the S-plane, you simply need to look at it, know that all the poles for your system that you're interested in are on that S-plane, and if the question is the system stable or unstable, all you need to answer is, are there poles on that right hand side? If the answer is yes, the system is unstable. If the answer is no, the system is stable. Done. As simple as that. For example, let's say that we have a very complicated system. It has 1,000 poles. 1,000 poles. That's a pretty nasty looking characteristic equation, as you can imagine, right? 1,000th order. 999 of those poles are on the left-hand side of the plane, and only one is on the right-hand side. So 1/1000th of the poles is on the right-hand side of that S-plane. But that one pole is really, really close to the y-axis, the edge of the imaginary axis. Let's call it, the pole is at 0 plus. You know, like when we do this limit thing, and we're just on the right-hand side of 0 type of thing, right? It's just at 0 plus. So in that case, the system is stable, right? Because like that pole is really close to the y-axis. So we're done. No, I'm kidding. This was a joke here to see if you were still paying attention. So just kidding. Remember, that's our test. Is it on the right-hand side? Yes or no? If it's at 0 plus, it's on the right-hand side. So no, this is not true. If it's on the right-hand side, even by a little bit, system is unstable. System is unstable. Again, remember, that means that we're going to have a term on the response of the system that's going to look like this for an A that is greater than 0. Yeah, that A might be really, really tiny, but positive. Well, time, waits for no one. Time is going to keep increasing, and eventually A times T is going to be a very big number, and E to that is going to be very, very big. So the system will blow up. Okay, so that's our first stability test. Do you have a pole on the right-hand side or not? The answer is yes, you're unstable. We don't always have a plot of those poles given to us, so we can't necessarily just jump to that test immediately. There are other tests that are worth defining at this point. First, for first and second order systems, a necessary and sufficient condition for stability is that there are no change in signs on the coefficient of that characteristic equation. So we already saw that little example of the first order system before that was unstable, where we had plus s minus 1 over tau is equal to 0. So we had a change in sign of the coefficient. The first order coefficient was a plus 1, and the 0th order coefficient was minus 1 over tau. That system is unstable. This is also true for a second order system, and I'm giving you a bunch of examples here to illustrate the point.
if I have a system that looks like 16 over s squared plus 18s plus 52, then that coefficient is plus 1. That coefficient is plus 18, and that coefficient is plus 52. Plus, 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 no sign change, stable. If I have a first order system and the characteristic equation is minus 3s minus 0.1, I've got minus, minus, system stable. If I have a second order system and first coefficient is plus 0.3, second is plus 17, plus 2, stable. Doesn't matter what's on the top, is what I'm getting at, okay? So those are all examples of stable systems. Conversely, unstable system, first order here, I got a plus, a minus, unstable. Second order system, I got a plus here, a plus there, good, minus there, bad, unstable, okay? Those are examples of unstable system, etc. So for first and second order, necessary and sufficient condition is that there are no sign changes in the coefficients of the characteristic equation. You can go to the bank with that. You don't even have to plot them on the S-plane. If you were to plot them on the S-plane, you'd find that you'd have at least one pole on the right-hand side. But you don't even have to do that. You simply have to look at the characteristic equation. Isn't that nice? Problem, though, is if the system is of a higher order than second order, say third order, all the way up, okay? Good news, in real life, we don't have a ton of physical systems that have characteristic equations that are of such high order. By and large, systems are up to third order maximum, and even then, we can usually split them down into products of first and second order and do a partial fraction expansion this way, and we can look at each component individually, and we come back to what we've had there. But if the system is very large, for whatever reason, if it's an exception to that rule, then we need to have a tool to determine whether or not it's stable or not, and this is what we're going to talk about here. Of course, nowadays you could simply take your characteristic equation, put it in Simulink, hit it with a step change, and observe what goes on, right? You could do this, but you're not always sitting at a computer running Simulink. You're not always sitting at a computer running Wolfram Alpha or something so that you can punch in a complicated looking characteristic equation and get all the roots so you can tell whether or not any of them are on the right-hand S-plane, right? And you're certainly not always given an S-plane with the poles plotted for you, like a silver spoon in the mouth kind of a deal here. So this doesn't always happen. So in the old days, we had a system for determining the stability, a necessary and sufficient condition for determining the stabilities of these complicated looking characteristic equations. Again, it's not as practical or imperatively important nowadays, but I find that it's a test that students really kind of gravitate to because it's very computational. It's like you feel like you're a computer when you're using it, and it's very efficient. It looks nasty, a little bit complicated the first time you see it, but it really doesn't take very long for you to wrap your mind around it and become very efficient at turning the crank and at analyzing system with it. And so as a student, I certainly loved using it, and I found that Cal Poly students also like to do it very much. And that system, or that method, is called the Ruth Array stability criterion. So it's a series of steps. Again, it's really algorithmic. It's like you are yourself turning into a computer, and you're going to run this test for yourself. So let's go over the test, and I think you'll see that's quite a cool system. Step number 0, once again, is to start with a characteristic equation. That's always the first thing we do. So in this case, of course, it's third order or higher. So I'm picking an arbitrarily high ordered one, an nth order system. That means the maximum power of the highest S minus the maximum power, the smallest power of the smallest S is equal to n. So the smallest S must be 0 and the highest S must be n, and that's what I got right here. This is our arbitrary nth order characteristic equation. Okay. So in order for it to be stable, it's going to be an if and only if all the roots of that guy, the n roots of that guy, are all on the left-hand S-plane. Okay. If any, so that's my first test, right? If I could get all of those roots, say by a computer or something, then and they're all on the left hand side S-plane, I'm done. Okay. Two, another important test that I can do rapidly here. The second one is actually I can do rapidly. The first one I got to find the root somehow. That's not necessarily easy. But a really easy test to determine instability is that if, again, there's any switch in the signs of the coefficients of that characteristic equation, right? So if a sub n is positive, a sub n minus 1 is positive, a sub n minus 2 is negative, I don't even have to go further. At that point, I know for a fact that the system is unstable, okay? If there's one switch in any sign at any point, that system is unstable, all right? The problem is, if I don't have any switch in any of the coefficients in that characteristic equation, I cannot conclude that the system is stable. In other words, it's only good to tell me for sure that the system is unstable, but if it's not unstable, I'm not guaranteed that it is in fact stable. Okay, it could be unstable but hiding under a series of uniform coefficients, if you will. So in order to get an absolute test in that case to determine whether or not the system is indeed stable, even though there's no switch in those coefficients, I have to develop what's called a Ruth array. And from that array, I will be able to determine absolutely the stability of the system. So step one in developing that Ruth array is to take that fancy looking characteristic equation, which we've got over here, and put all the coefficients of that array on two separate rows. The first one starts with the highest order coefficient, okay? Then I skip one, then I put the second coefficient after that, then I skip one, then I put the fourth coefficient after that, etc., right? So every second coefficient goes into the first row until I get down to zeros, right? Because I got nothing else. And in the second row, I put all the other alternative coefficients. So it's a little bit like I'm starting with the first one on the first row, then I go to the second row and put the next coefficient, then I jump back to the top row and put on my third coefficient, then my fourth coefficient goes back down on the second row, etc. Okay? And so I populate my two rows like this until I've taken care of all my coefficient, meaning the s to the 0th powered coefficient is included if I have one. Okay, so that's the beginning of my Ruth array. So far, so good. Then I'm going to continue to populate an array depending on how many coefficients I have, by writing on the left-hand side of the margin each of those coefficients. And I may or may not go all the way down to the s to the 0, but I will never go below s to the power of 0. So that gives me a limit to how many rows I'm going to have on this system right there. And to illustrate how I find the coefficients that go into each of these rows now, this is where the algorithm comes into play here. So to calculate these coefficients, B's for row number 3 and C's for row number 4, the way I've got it right here, the first step is to take the coefficient on the row that's immediately above it. So in the case of the third row, I'm going to take the coefficient of the row that's immediately above it in position 1. Okay, so the leftmost column of the row that's immediately above it, times minus 1. So for coefficient B1, that's going to be minus 1 divided by a sub n minus 1, because that's the coefficient in the row immediately above it on the far left side of it, the first coefficient on that row. And I'm going to multiply it by a determinant, and the determinant is going to be made up by the 4 coefficients that are immediately above it in this particular case. Okay, things are going to change in a moment, but for the very first one, the B1 term, it's the ones that are immediately above it. Okay, for this, and so the determinant, if you don't recall, is going to be the product of the top left term with the bottom right term minus the product of the second row first column term times the first row second column term over there. And that's what I've got over here. Okay, so I got to compute that guy, and that's going to give me what goes in for B1 on my array up there.
For the second b, all right, same thing. I'm going to have the minus the negative of the term in the row right above it in position 1, so that still is minus 1 divided by a to the n minus 1. But the determinant that I take now is what's immediately above my my term, which now is b2 times a determinant that's made up by the first column term and the column that's immediately next to the coefficient that I'm interested in. So in the case of B2, the next column to the right of the column that B2 is on is going to be column 3. And so the terms that I'm going to have on my determinant for my second column are going to be an minus 4 and an minus 5. And that's what I've got over here. Okay. My first column is the same as the one I had above. So for all the b's, the first column of my 4-term determinant is always going to be the same terms, an and an minus 1 on my first column. Okay. Again, I compute the determinant and I multiply it by minus 1 over an minus 1. I get something. Okay. And then, so that pattern right there continues to repeat itself. If I had a B3 term, if I needed to calculate a B3 term, that's going to be minus 1 over an minus 1, right? Which is, again, the term above it, first entry on that row, times the determinant of an minus 1. Cleaner here, an minus 1. Where's my b's there? B3. Okay, so this is this guy right there. I've done it. And times the terms that would be right here, and that would be, let's write them out, an minus 6, an minus 7. So an minus 6, an minus 7. Okay, and well, I've got B3. Okay, you get the idea. Repeat that for C. The first term in the row immediately above it is going to be B1, and so therefore my coefficient is going to be minus 1 over B1, and I'm going to build that determinant in the very same way. Okay. All right. When I'm done doing all this, the only thing that matters is the sign of the coefficient in that first row. Sorry, first column. So let me clean this up a little bit here. Okay, I don't need all that stuff. Need that. So first column is what matters. I'm going to look at the signs as I go down this column. So let's say that A1 is positive, right? In other words, my characteristic equation is all positive. It has to be, because if A1 and an minus 1 were not of the same sign, then I wouldn't have to do this whole thing. I would know the thing is unstable. So this guy's positive, this guy's positive, this guy's positive, this guy's positive. All of the coefficients in that first column must be positive for the characteristic equation to have only roots in the left-hand plane. Is that neat or what? If there's any sign that changes, the system's unstable. As simple as that. How many roots will I have on the right-hand S-plane as a result of that? As many roots as there are sign changes in that first column. So not only do I know whether the system is stable or unstable, okay, I know how many roots there are on the right-hand S-plane. Do I know what those roots are? No, sorry, you don't. Okay, it doesn't tell you where the roots are. It simply tells you that there are some on the right-hand S-plane and how many there are. You're going to have to do some math to figure out what they are later on if you're interested in that. But very often we're just interested in determining whether or not the system is stable. And that's it. That's all you got. So the first question that probably comes into use is, well, that's great, but what if one of the elements on that first column is a 0? Is that a plus or is that a minus? What do I do there? I mean, how do you know whether it's a sign change or not? In that particular case, and trust me, it happens quite often, you replace the 0 with epsilon. And infinitesimally
approximately small positive number. Okay, so in the case of the example we just had there, A1 was positive, AN was positive, AN minus 1 was positive, blah, 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 blah. The third one is, say C1 is 0. I would replace C1 by epsilon, a positive, very, very small number, and I would keep on going. Okay. You see how that's important because I'm in the first column and have epsilon, a very small positive number. What's going to come in column D, row D, the row just below it, I'm going to have a minus 1 over epsilon, an arbitrarily small number that I'm going to multiply by some determinant. But minus 1 over epsilon is going to be an infinitely large negative number. So that determinant, the sign of that determinant is going to determine everything else that happens at that point, right? All right. So recapping on the necessary and sufficient conditions for Ruth Criterion, there's no change in the sign of the elements on the first column. The number of sign changes equals the number of poles in the right-hand S-plane. If all the elements in a row are 0, then the system has poles in the right-hand S-plane. Okay, that's in the case where I'm not done of doing my analysis here, but I still have one row that sticks out with all zeros in there. Okay, and so this can happen if, like, I have a 10th order, characteristic equation, and like a lot of the second terms are zeros, so I'm going to have a row with a lot of zeros in it because, you know, I'm skipping a lot and I'm getting a lot of zeros in there. Okay. All right. Let's do a quick example here and see if you agree with me here on how that works. So we've got ourselves a system whose characteristic equation is s to the 5 plus s to the 4 plus 6s cubed plus 5s squared plus 12s plus 20 is equal to 0. Is that system stable or not? So I'm starting, so first of all, step number 1, is there a sign change going on in the characteristic equation? No. Okay, I've got plus S5 plus S4 plus S3 plus S2 plus S to the 0. No sign change. So I can't conclude anything just based on that. So when I'm stuck in that situation and, you know, just looking at it, I don't have a computer in front of me. Well, I do, but you know what I mean? I can't just do a lookup of what the roots are. Somebody's asking me this. I have to build that Ruth array if I want to answer that question rapidly. So I'm going to build that Ruth array right there. I've already started. And so that very first term that I have in there in my top row, I'm starting at S5, my second row is S4, my third row is S3, S2, S1, S to the 0. That's at most I'm going to have 6 rows in this thing. I'm probably going to have fewer, but let's start with that. I'm building my array to begin with by entering each row one at a time. The first one is going to be the coefficient of my highest order term, which is S5, so that's a 1. Below it, on row 2, is the coefficient of my second highest term, S4, which is also a 1. Back to the top, which is, let's see, let me plot this here so you guys can see where I'm going. Back to the top, I went down, back to the top. On my first row is the coefficient of the S cubed term, which is a 6. Back down, coefficient of the S squared term, 5. Coefficient of the S term, back on the first row, is 12. Coefficient of the S to the 0 term on the next row is going to be 20, and then I'm done. And for the sake of calculating my determinants, I can keep populating the array with as many zeros to the right of this as I need, and so I'm going to add a few up there. Okay. Next, we need to calculate this term right there, which above I called B1. This term is going to be B2, B3, B4. You can tell what B4 is going to be, right? Because I'm going to end up with a determinant that's going to be 6, 5, and 0, 0. If I have a column of zeros in a determinant, I'm always going to have a 0. So B4 for sure is going to be 0. Okay. In fact, B3 with this 0, 0 right there is also going to be 0. So really, I just need to worry about B1 and B2. Let's figure this out. B1. So B1 is equal to minus 1 over the term immediately above it, which is 1, times the determinant of the first column immediately above it, which is 1, 1, times the column immediately to the right of it, which is going to be 6, 5. Okay, so that's equal to minus 1 times 1 times 5, which is 5, minus 1 times 6, which is 6, like this. And that looks like minus 1 times minus 1, which is plus 1. So B1 is plus 1. Put that in right there, plus 1. Okay, B2, let's do B2. B2 is equal to minus 1 times the term in the first column immediately above it, which is again minus 1. That's not going to change as we move along, as we said, times the determinant of the first column above it, which is 1, 1, and the column immediately to the right of it, which is 12 and 20. So that's minus 1 times 20 minus 12. Ooh, okay. 20 minus 12, which looks like minus 8. Minus 8. Okay? That's B2 though, it's not B1. So it's not in the first column. So the fact that we have a sign change here is not as alarming as if B1 had it. Well, alarming, depends on your point of view, right? If my goal was to figure out if it was stable or unstable and I had that minus 8 in that first column, I would be done. I wouldn't have to keep going with the Ruth array. These guys, the fourth row, which I've called C1 before, let's do that again. C1 is going to be minus 1 over the term above it, which is a 1, times the determinant of the column made up by the 2 rows above it, which is going to be 1, 1 again in this case, and then 5 and minus 8. So that looks like minus 1 times 1 times minus 8 is minus 8 minus 5. So that is plus 13. And again, again, I have a positive term. So far that system is stable. C2 minus 1 times the determinant of 1, 1 times, let's see, these two guys right there, which is going to be 20 and 0. So that's going to be minus 1 times 0 minus 20, which is going to be plus 20. So that's C2 plus 20. Okay. We've already said that B3 and B4 were 0 here, right? So let me put those in there. 0 and 0. And C3 is going to be a determinant that's going to have these two guys right there. So that's also definitely going to be 0. All right, we're down to the D's now, the row below it. Let's call that D1. And that's going to be minus 1 over 13 now, times the determinant of the two terms above it, 1 and 13, and the column immediately to the right of it, which is minus 8 and plus 20, which is minus 1 over 13 times 20 minus 8, minus is going to be plus 8 times 13. Well, that looks like that's going to be a negative number, right? 20, let's see. Yeah, exactly. So when I do the math on this guy here, I am going to get minus 113 times 20 times 8 times 13, which is 104. 20 plus 104 is 124. This guy is going to be minus 124 over 13. So really, my only question was, is the system stable or unstable? I am done here. The system is unstable, minus 124 over 13. But let's say that I kind of needed to keep on going here. Again, for the term, the second term next to this, which is going to be my D2 terms again, I got 0, 0 on the two on column number 2 on my determinant, so therefore that guy's going to be 0 as well. That's easy. So I'm left with just this last guy here on row S to the 0, and I'm going to call the E1 term. E1 term is going to be minus 1 over the term above it, which is 13 over 124, times the determinant of what's above it, which is 13 minus 124 over 13, and then 20 and 0. Okay. And I did the math on that already here, and so I get plus 20 over there. So this guy here is plus 20. Okay, well, we've already established that the system is unstable. So let's answer the question here. Is the system stable or unstable? The answer is unstable. And if it's unstable, how many poles are on the right hand side of the S-plane? And we have as many poles on the right hand side of the S-plane as we have sign changes on that first column of the Ruth array. And let's be careful here on how we count this. A lot of people make that mistake when they do this. But the first term is plus 1. The second term is plus 1. No sign change. The next term is plus 1. No sign change. Next term is plus 13. No sign change. The next term is minus 124 over 13. One sign change. And then the last term is plus 20. So I went from minus to plus again. Another sign change. So therefore there are two sign changes in the first column. And so therefore 2 poles on the right hand side. That answers my question. All right, I prepared a last example here, but I'm running out of steam here. We're just at about the 1 hour mark. So let's just call it a day. I'm going to let you do it. Not to give the cat away here, but this last one is a little bit of a treat. This other example, you're going to get to use that epsilon rule that we just talked about before. In other words, you're going to end up with a 0 in that first column. So see if you can figure out whether that system is stable or not. All right, we're good. Have a good rest of your day. I hope you enjoyed the lecture, and I will see you back in class on Monday. Take care. Bye-bye.